So here's a question on kinetics, and this is referring to the kinetics of a rigid body, and it actually combines a couple of concepts. One of them is this idea of the no-slip condition, and it also uses the Suvet equations that we're going to use a bit later. But first, let's read the question. Let's see what it's all about. So there's this truck, and there's a solid cylindrical roll of paper, right? This is what the question tells us, and this is loaded onto the back of the truck, and the truck starts moving forward, right? It starts going to the right with a constant acceleration that's given to us as a. And what we have to find is the distance s that the truck moves before the paper falls off the edge. Okay, and the key thing here is that friction is sufficient to prevent slipping. So let's discuss this no slip condition and what it means. So generally, a lot of students think that no slip means that the velocity of this cylinder or of the sphere or the circle that's rolling is equal to zero, right? Which in a lot of cases it's true, but the definition goes a bit beyond that. So if this surface here was something like a conveyor belt, right? In this case, in our case, it's a truck that's moving. But let's assume this is a conveyor belt with a certain speed v. Then clearly, if this cylinder, if this point on the edge has a velocity of zero, while the conveyor belt has a velocity of v, which is non-zero, there will be some slipping effects occurring. So for slipping to not actually occur, we must actually have the velocity of this point to be exactly equal to the velocity of the surface, right? And this is actually what no slip means. So whatever the velocity the surface has, that's exactly the velocity of the outer edge of the cylinder, which is in contact with the surface. Okay? And in our case, this helps us because we know the truck moves to the right with an acceleration of a, which means that the horizontal acceleration of point O, which is sitting on the cylinder, has to also be equal to A. Okay, so point O actually has two components of acceleration. There's one that goes to the right, which is A, and there's another one which goes in the vertical direction. But as you'll see, we won't really care too much about that. So let's try to use this information to maybe try to find the acceleration of the center of mass of the cylinder. So if I redraw the cylinder here again, so we've got point C and then we've got point O, and then I'll put my coordinate system like this. So I've got my X, I've got my Y axis, and using Euler's equations for acceleration, I have that the acceleration of point C is equal to the acceleration of point O plus alpha cross product with OC and then minus omega squared OC. Okay, so this is what we're trying to find, and we know because the cylinder is moving, or we know that the center of the cylinder is moving along a straight line. This acceleration only has an x component. So this is AC times I only, okay? Now, AO, on the other hand, this has two components. So one of the components is the acceleration of the truck, which is AI, and the other one is the acceleration of O in the normal direction times J. Okay? And then we have this term, which is uh, found by calculating this determinant. So we've got IJK and then 0, 0, and then the angular acceleration, which we don't yet know. And then OC is the radius, right? And in other words, it's actually this vector right here, which is in the positive direction, and it's in the positive y direction. So it's going to be 0, and then r, and then 0 again. Okay? and then we have minus the final term, which is omega squared OC. OC is once again our radius, which is in the y direction. Okay, so the only thing we're trying to find now is this acceleration, which we can get by, first of all, solving this determinant. So let me rewrite everything. We've got AC times I equals AI plus the normal component of O plus, and this is going to be I times, and then if we do this determinant, we're just going to get minus alpha R, and then we draw a line here, minus omega squared Rj. Okay, AC only has an x component, so we can equate the x components on the left with the ones on the right. So we have that AC is the only one on the left, and then on the right we have A, and then we have minus alpha R here, which means that the acceleration of the center of mass is going to be equal to A minus alpha R, which is good, and I'll call this equation 1. But it doesn't really help us to solve the whole question because we don't know a couple of things. Well, we don't know AC, obviously, but we don't even know the angular acceleration, and we don't even know the radius of the cylinder either. But as you'll see in a second, we won't actually need the radius of the cylinder. Um, so the other thing we can do is we can write Newton's second law for the cylinder. So as the cylinder is sitting on the truck and as the truck is moving, so is the cylinder. And the reason for that is because there is friction. Right? The question tells us there's friction. There's also no slipping that's occurring. So let's see how that helps us. So we've got weight, we've got the normal reaction force, and then we've got friction. And friction on the cylinder is acting to the right. Okay? By the way, one important thing to note is that in this case, friction is not equal to mu times m because this is not kinetic friction. Okay, there's no slipping between the two surfaces. So how can we use that? So first of all, we're going to write Newton's second law for translation, which is simply Ff is equal to the mass of the cylinder multiplied by the acceleration of the center of mass, which is exactly the same as the AC that we found previously in equation 1, right? And the other thing we're going to do is we're going to apply Newton's equation of motion for rotation. So this will give us the sum of moments where counterclockwise is going to be positive, is going to be equal to the moment of inertia in the above the z-axis multiplied by the angular acceleration. Okay, so the only force above the center of mass which produces a moment above the center of mass is friction. So that will give us that friction multiplied by the moment arm, which is r, is equal to the moment of inertia. Now, the moment of inertia for a cylinder, you can look it up, or maybe you even remember it, is actually 1/2 mr squared. And this only works if the cylinder is solid, as the question tells us. Okay, and then we have multiplied by alpha. So we've got three equations here. The first one tells us that friction is equal to mass multiplied by AC. And the other one, we can actually simplify one R here. And this equation tells us that Ff, the friction, is equal to 1/2 mr alpha. So 1/2 mr and alpha. So we can substitute for friction. So what this gives us is that m times AC is equal to 1/2 mr alpha. We can cancel out the m's. And what we get is that AC is r alpha divided by 2, or we can rearrange this to find alpha, which is 2 AC over r. And I'm going to call this one equation 2. So I'm going to take equation 2 and I'm going to use it to put it back in equation 1 and get something useful out of there. So equation 1 said that AC was equal to the acceleration A minus alpha r. But instead of alpha, I'm just going to substitute what alpha is. And then we have the r that we multiply here. And then we can cancel out the r. So as you can see, r is not actually part of the problem anymore. And then we can rearrange and we get 3ac is equal to a. Therefore, the acceleration of the center of mass of the cylinder is a over 3, is a third of the acceleration of the truck, which actually means that the truck moves 3 times faster than the center of mass of the cylinder. So let's see how that helps us to find the distance traveled by the truck. So what I'm going to do here is I'm going to draw, this is the trunk sort of before the truck starts moving, let's say. So you've got the cylinder sitting here, and then when the cylindrical roll falls off, the truck moves a certain distance, and now the cylinder is here, right? So in other words, it starts here and it ends here. So this is what I just drew, but as seen from the, let's say, the right hand side of the truck as it's going past you, right? So what we have is we have this distance is given to us as d, right? This is known, and what we have to find is this distance s that the truck moves. Okay, so we're trying to find s, and to do that, I'm going to write the Suvet equation for the truck. Okay, so we know the acceleration of the truck. So we have that the distance that the truck moves until the roll falls is equal to 1/2 a t squared, because the truck moves with an acceleration a, and I'm saying there's also a certain amount of time t until this point here is reached. Okay. Now we can't technically find s because we don't know t, so we have to find t from somewhere else, and that somewhere else is going to be the Suvet equation for the center of mass of the cylinder. Okay, so before it falls off, the cylinder moves a distance s minus d. Right, this is what the diagram is showing us. So here's what we have. We have s minus d is equal to 1/2, and then we just found the acceleration of the cylinder as a over 3. So that's what I'm going to write here. So we have a over 3 t squared. So that will give us t, or t squared. So we can see that we have two equations with two unknowns. So from the first equation, we can take out t squared. So t squared will just be 2s over a. And we take this t squared and we put it back into the second equation, and this is what we will get. So s minus d is equal to 1/2 times a over 3. So it's going to be 1 over 6. So 1 over 6a, and then instead of t squared, I'm going to write 2s over a. So 2s over a, and well, in this case, the acceleration a is going to go, and the 2 cancels out with the 3 here, and we're going to, with the 2 cancels with the 2, and we get a 3. And finally, we end up with s minus d equals s over 3. Which means that if we rearrange this, s minus s over 3 is equal to d, therefore 2s over 3 is equal to d, therefore s is equal to 3d over 3. And this is the distance that the truck travels before before the cylindrical roll falls off. And as you can see, the result tells us that this distance doesn't depend on the acceleration of the truck or the mass of the roll or anything like that. It only depends on how big the or how long the trunk is, basically. And it's 1.5, the length of that trunk. Um, and the condition for that to happen is this right here. So we must have this no slip condition present. And if that happens, it turns out that this distance traveled only depends on the size of the truck, basically. So yeah, that's the problem.